Welcome to the third lesson of the fifth module, which is on bending of beams part 3. In fact, in the last two modules or in the last two lessons, we have discussed some aspects of the bending of beams. We have looked into the concept of shear force and the bending moment. Now, in this particular lesson, we will see that how to evaluate the variation of shear force and bending moment along the length of the beam, and the related aspects will be discussed in this particular lesson. Well, once this particular lesson is completed, it is expected that one should be able to understand the concept of shear force and bending moment diagrams. Now, as we have seen so long that we have calculated the shear force and the bending moment in a beam at a particular location along the length of the beam. Now, if we like to find out that how the shear force is varying along the length, or if we like to have the variation of shear force at any point along the length of the beam at a glance, then we need to draw a diagram over the length, the variation of shear force and the bending moment, which we call as a shear force and bending moment diagram, which we will look into in this particular lesson. And one should be able to evaluate the reactive forces, the shear force and bending moment for different types of beams, which we have discussed earlier, and for different types of loading that the beam will be subjected to. And consequently, one should be in a position to plot shear force and bending moment diagram of beams for different loading and for different kinds of support conditions. Hence, the scope of this particular lesson includes recapitulation of previous lesson. As we do, we will be looking into the aspects which we have discussed in the previous lesson. Then the concept of drawing shear force and bending moment diagrams. Now, in this particular lesson, we will introduce that how we can plot the variation of shear force and bending moment along the length of the beam, which we define as a shear force and bending moment diagram. And examples for evaluation of reactive forces, shear force and bending moment for different beams under different loading conditions, and plot of SFD is shear force diagram and BMD is bending moment diagram. So, we will look into the how to plot the shear force and bending moment diagram of a particular type of beam, that means a beam which is supported on a particular kinds of supports which we have discussed and subjected to loading of different kinds as we have discussed in the previous lessons. So, let us look into now, before we go into the details of shear force and bending moment diagram, let us look into the questions which was given to you last time. Now, the first question was that for a uniform loading, that means, if a beam is subjected to uniformly distributed load on a portion of a beam, then what will be the variation of shear force in that particular part of the beam. Now, let us look into the discussions which we had in the last lesson, wherein this is the part of a beam. Supposing if we have a beam which could be a simply supported one, hinged at this end and supported on roller at this particular end and subjected to uniformly distributed load. Now, if we take a part of this particular beam of length d x, then according to our conventions we have placed the shear force and the bending moment on two sides. Now, this particular equation we have seen in the last lesson that dV dx is equals to q. Now, the question is, if q is constant, if it is uniformly varying over the length of the beam, then what is the state of the shear? Now, if q, as we have seen earlier, that if q is equals to 0, then the shear force is constant. Now, if q is constant, if we have uniform loading over a part of the beam or over the whole beam, then the shear varies linearly in that part of the beam. And in fact, if you remember, for a simply supported beam, if q is the uniformly distributed load, and since we do not have any horizontal force, so the reactive force which we will have at this hinge support is a vertical one. If we call this as A and this as B, so this is R A and this is again a vertical support which is R B, and this being symmetrical, we can write that R A is equals to R B is equals to Q times L is the total load. So, half the load will be carried by reactive force A and half the force will be carried by reactive force B. So, R A equals to R B equals to Q L by 2. Now, if we try to calculate, if we take a free body at a distance of x from A, then if we take the equilibrium of the forces of this free body, now here we have R A, on this part of the beam we have Q and this distance is x, and the resultant stress resultants at this particular end is V here and moment M here. So, since we are talking about shear force V, V is if we take the vertical equilibrium V plus R A minus Q times x is equals to 0. So, this gives us that V is equals to Q x minus R A is Q L by 2. So, the variation of V here, as you can see, it is a function of x, and x is linearly varying in this particular equation. Hence, the variation of V will be linear when we have uniformly distributed load, and this in fact we will discuss further through the examples, and you will see that over the length of the beam, if we have uniformly distributed load, then what is the value of the shear at different locations along the length of the beam. Now, the second question was, what is the effect on bending moment if shear force on a portion of beam is 0. In fact, this aspect also we have discussed, and to do that, let us look into this particular equation. When we take the equilibrium of the bending moment on the left edge of that particular segment, then the resulting equation comes as dm dx is equals to V, or the rate of change of the moment along the length of the beam is equals to the negative of the shear force V. Now, if this quantity becomes 0, if shear force is 0, then m is equals to constant. So, the portion in a beam where the shear force is 0, the bending moment at that particular portion will be constant, and this is an important observation, and this will be helpful when we will be drawing the shear force and the bending moment diagram. Now, the last question which was given was what is the effect of concentrated load at a point in a beam on bending moment at that particular point. Now, if you remember, in the last lesson we had discussed the effects of different kinds of loads on the shear force and bending moment at a particular section, and the loads which we had considered were the uniformly distributed load, the concentrated load, or the concentrated moment. And where we had the concentrated load in a particular segment, we had evaluated the shear force on the left of that particular load, and we had evaluated the shear force bending moment on the right of the particular concentrated load. And as you have noticed that when you have this concentrated load, the change in the moment, the expression for the moment on the right side, on the left side of the load we have shear force V and moment m. On the right hand side, the moment is m plus m1, where m1 is given by this particular expression. Now, here since the quantities are multiplied with this small value dx, hence it is expected the value of m1 is significantly small in comparison to m, and hence at a location in a beam where there is a concentrated load, if we try to evaluate the bending moment on the left of this concentrated load and on the right of the concentrated load, we will find that there is absolutely the change is very insignificant, and we can neglect that, and we can say then that at the point of the concentrated load, the variation of the bending moment on the left side of the load and the right side of the load is absolutely small and can be neglected. But what happens is that there will be change in the rate of change of the moment. Now, on this side, as we have seen that dm dx is equals to minus V. Now, on this side we have V, and on this side we have V plus V1, and as we have seen from vertical equilibrium that V1 is equals to P. So, on this side the rate of change of moment dm dx is equals to v plus v 1 or the negative of the whole thing. Now, here there will be a change of the order of p from the left hand side. So, though there is no change in the moment or there is insignificant change in the moment value from the left hand support of the concentrated load point to the right hand part of the concentrated load point, but there is significant change in the rate of change of the moment. So, dm dx will undergo change when you have a concentrated load, and that again we will be looking into through the examples. Well, then in general, as we have observed from these expressions that dv dx we have seen as equals to q and dm dx we have seen as equals to minus v, and if q is 0, then the shear is constant as we have seen through the examples as well, and if q is uniform, then shear is linearly varying along the portion of the beam. If q is constant, then shear will vary linearly. Just now we have looked into that. Also, the change of shear between 2 points is equal to the area of the loading diagram. Now, if we look into this part of it, that from this particular equation we can write dv is equals to q dx. Now, if we integrate this expression between 2 points, supposing we take 2 points on the beam, let us say this is A and B at a distance apart, and if we like to find out the change in the shear force between A and B. So, integral dv from A to B is equals to integral from A to B q dx. Now, this gives us that integral dv from A to B is basically shear force at B minus shear force at A. So, the differential shear force between B and A, this is nothing but equals to q dx represents the area of the loading. As you can see on the beam, when we have the distributed load, this is q and over the length dx, this gives the area of the loading. So, integrated between A to B, this is nothing but the area of the load between points A and B, and that is equals to the difference in shear between point B and A. So, on the beam, if you have uniformly distributed load, then the difference in shear between these 2 points B and A is equal to the area of the loading diagram between B and A. Now, from this particular expression that dm dx is equals to minus v, if shear force is equals to 0, then bending moment is constant, and this is what we have observed right now. Now, if we like to calculate the change in bending moment between these 2 points B and A as we have done for the shear force, then what we get? Now, here if you integrate it again, integrate dm over the region A to B, this is equals to integral minus v dx from A to B. Now, here integral dm from A to B is the bending moment at B minus bending moment at A. So, the differential bending moment between B and A, this is nothing but equals to, now B, which is a shear force, could be a function of x as well. So, this basically gives us, when we try to plot the variation of the shear force, we can have a diagram of shear force, and that integral v dx precisely indicates the area of that shear force diagram, and that in fact we will be looking into as we go along for the shear force and bending moment diagram. Now, at the point of concentrated load, there is change in shear and rate of change of bending moment, that is what we have observed right now, and at the point of concentrated moment there is no change in shear, but there will be change in the bending moment. So, these are the different kinds of loading as we have looked into, and their relationship with the shear and the bending moment can be summarized in this form. Well, now these aspects which we have discussed, now let us look into those criteria through this particular example. Now, here in fact this particular example I had given to you last time for your solution, let us look into that what information we can extract from this particular example. Now, a simply supported beam AB is loaded as indicated over here. What we need to do is that we will have to evaluate the shear force and bending moment at AA and BB. Now, two sections are marked, two locations are marked AA and BB. At these two locations, we will have to find out the shear force and bending moment. Now, please note over here that AA and BB are no fixed location as such. That means, we have not given any fixed dimension for this, and let us call this as a variable dimension which is x, and this also a variable dimension which we call as x. Now, question is we will have to find out the value of the bending moment and shear force at AA and at BB. Now, here again as we do not have any horizontal loading. So, the reactive force at A, which is horizontal and vertical, the horizontal component will be equals to 0. So, here we have the vertical component, we have the horizontal component, and here we have the vertical component. Now, this horizontal component will be equals to 0, since we do not have the horizontal force. Now, the free body diagram of this particular beam will look like this, and let us call this as H A, let us call this as R A, and this the reactive force as R B. So, summation of horizontal force equals to 0 gives us H A is equals to 0. Summation of vertical forces equals to 0 gives us R A plus R B, this is equals to 0. Sorry, this is not equals to 0, because here we have the load which is uniformly distributed. So, this is not 0. So, this is equals to what, as 8 kilonewton per meter multiplied by the length 5 meter. So, 8 into 5, so much of kilonewton. So, 40 kilonewton is the value for R A plus R B. Now, we need another equation for evaluating these two unknown quantities R A and R B. Now, if we take the moment of all the forces with respect to this point A, let us say summation of moment with respect to A is equals to 0. So, if we take the moments of all the forces, now R B into 5 plus 3 is 8 meter, which is acting in an anticlockwise direction. Then we have an external moment which is also acting in anticlockwise direction and which we have considered as positive. So, this is 12 kilonewton meter, which is anticlockwise direction, and then we have this loading which is acting at the center of this length, and this is causing a moment which is in the clockwise direction. So, minus 8 into 5 times 2.5. So, this is the moment and this is equals to 0. So, this gives us that R B times 8 plus 12 minus this is 5 times 8 40 times 2.5 is 100, this is equals to 0. So, this gives us a value of R B as equals to 11 kilonewton. Now, since R A plus R B is equals to 40 kilonewton and R B alone is 11 kilonewton. So, R A is equals to 40 minus 11 is equals to 29 kilonewton. So, the reactive values R A is 29 kilonewton and R B is 11 kilonewton. Now, what we need to do is that we need to evaluate the value of shear force and bending moment at section AA and section BB. So, let us cut the beam at section AA and let us take the free body diagram of this particular part and see that what are the values of shear force and bending moment we get. Now, if we do that, the free body diagram of the left hand part is, here we have R A which is 29 kilonewton, we have the uniformly distributed load which is 8 kilonewton per meter, and this is the distance which we call as a variable distance x, and here we have the stress resultants V and bending moment M. and this is the section AA. Now, if we take the equilibrium of the vertical forces, then we have V plus 29, which is R A, minus 8 into x over the length x, this is equals to 0. So, the shear force V is equals to 8 x minus 29. Now, if you calculate the bending moment here, if we take the moment of all the forces with respect to this point or section AA, then we have moment M, which is in the anti-clockwise direction. Now, R A will cause a moment in the clockwise direction. So, minus 29 into x, and the load will cause a moment in the anti-clockwise direction. So, this is plus 8 into x by 2. So, 8 into x square by 2. So, this is equals to 0. So, the bending moment is equals to 29 x minus 4 x square. So, this is the value of the shear force 1, and this is the value of the bending moment. Now, if we look into that from this particular expression, if we take the derivative of this moment dm dx, this is equals to 29 minus 8 x, which is nothing but equals to minus v, and this conforms to the expression as we have seen earlier, the relationship between the shear and the bending moment and the loading between the shear and the bending moment. Now, if we try to calculate the value of the bending moment at the limiting point, in a sense that here the bending moment, if we compute at this particular point where the uniformly distributed load comes to an end, and there we have a concentrated moment, and on this part we do not have any loading. So, let us see what is the consequence to that. Now, the distance x, if we substitute this as equals to 5, where the uniformly distributed load ends, then the moment at a distance x equals to 5, this is equals to 29 into 5 minus 4 into 5 square. So, this gives us a value of 45 kilonewton meter. Now, what happens is that the moment at that particular point is equals to 45 kilonewton meter. Now, let us calculate the value of the bending moment and shear force at section BB. Then you can compare these two and see what happens if we have what happens to the shear force when there is no loading into it. Now, let us take the free body diagram of the part which is at section BB. So, here again we have the shear force V, the bending moment M, and we have the uniformly distributed load up to a distance of 5 meter, and here we have the reactive force which is 29 kilonewton. So, this is 8 kilonewton per meter, and this is a distance of 5 meter. Now, this is a distance which we have chosen as x, which is a variable distance, and this particular section is BB. Now, if we take the vertical equilibrium of all the forces, we have V plus 29, which is R A, minus, now here the whole loading acts, which is 8 kilonewton per meter over the length 5 meter, we have 40, and at this point mind that we have a concentrated moment which is 12 kilonewton meter. So, this is equals to 0. So, we get V as equals to 11 kilonewton. Now, you see that this is a constant quantity. So, beyond this particular loading point up to the end of the beam, the shear force is constant, and please note that over this particular part of the beam we do not have any uniformly distributed loading, and as we have seen that dV dx is equals to q, and if q becomes 0, then V is constant, and that is what we are observing over here, that the shear force V is equals to 11 kilonewton, and whichever section you take up to the end of the right support, everywhere you will get the same value of the shear force. Now, if you compute the value of the bending moment at this particular section, then taking moment of all the forces with respect to this particular section B B, we have m, which is anticlockwise direction, then the contribution of the moment from R A is in the clockwise direction. So, m minus 29 x, and this also in anticlockwise direction. So, plus 8 into 5 into 5 by 2. So, 5 square by 2, and we have a concentrated moment which is also anticlockwise direction. So, this is 12, this is equals to 0. Now, from this we have m is equals to 29 x minus this is 100 minus 12. So, this gives us a value of 29 x minus 112. Now, what happens here is that there is a immediately change in the value of the bending moment as we go from this end to this end, because we have a concentrated moment over here. So, if we substitute the value of x as 5, then this is equals to 145, and 145 minus 112, this is equals to 33 kilonewton meter. Now, what happens is that on the left hand side, which we had calculated from the previous expression, you had obtained that the bending moment at this particular point, we have looked into that the bending moment at this point was 45 kilonewton meter. Now, that was the limiting point. From this end we had considered a section, the section was valid up to this particular end where the concentrated moment is applied. Now, immediately after this concentrated moment, when we take the effect of this concentrated moment, we find that the moment value has come down to 33 kilonewton. So, there is a jump in the bending moment value, but there is no change in the shear force value, and this is what we have observed when we have looked into the effect of a concentrated moment in the span of the beam and the effect of that concentrated moment in the change in shear force and the bending moment. We find that there is absolutely no change in the shear force, but the value of the bending moment changes immediately from the left to the right part of the concentrated moment. Well, now having looked into this, having looked into the aspects of the relationship between the different kinds of load and the shear force and the bending moment. Now, as I have told you that our objective for these kind of members which are subjected to loads is to evaluate finally the stresses, and if we like to find out the values of the maximum stress that occurs in the beam for such loading, we must know that what is the maximum magnitude of the bending moment of the or the shear force that is acting. Now, to know precisely that where the maximum bending moment or the maximum shear force is acting, or let us call that the value of the bending moment or the shear force which are largest in magnitude, if we try to find out that, we must know the variation of shear force and the bending moment along the length of the beam, and that can be done if we can plot the variation of the shear force or the variation of the bending moment along the length of the beam. Then we can say, well, immediately at this particular point we have the maximum value or the largest value of the bending moment or the largest value of the shear force, based on which we can start evaluating the stresses. Now, to do that, to find out the variation of the bending moment or the shear force along the length of the beam, the diagram which we plot, we call those as shear force and the bending moment diagram. So, this is what it is defined here, is the graphs in which shear forces and bending moments are plotted in ordinates against distance x along the length of member as abscissa. Now, what we do is that the magnitudes of the shear force or the magnitude of the bending moment we place in the ordinates, and the distance x, any distance x from the beam, if we like to compute the value of the shear force or the bending moment, and that if we place in the abscissa, then the graph which we get gives us the plot of the shear force or the bending moment or the variation of the shear force and the bending moment along the length of the beam, and those diagrams of the graphs we call as shear force and the bending moment diagram. So, for convenience what we do, supposing if we have a simply supported beam, now we choose our coordinate axis in such a way that abscissa lies along the axis of the beam and the ordinate is perpendicular to the axis of the beam. And here if we plot the shear force or the bending moment ordinates along the length of the beam, then the plot which we get, this diagram we will call as shear force diagram or bending moment diagram if we plot the ordinate the bending moment ordinate into it. So, this is how we can arrive at the variation of shear force and bending moment along the length of the beam, and this in fact we will explain now how shear force and bending moment diagram can be plotted for different kinds of loading, for different kinds of beam supports or different kinds of beams, as we have categorized either simply supported beam or a cantilever beam, that we will look into that how we can evaluate the values of shear force and bending moment and how we plot the shear force and bending moment diagram. Now, let us start explaining this concept of shear force and bending moment diagram or how to plot the shear force and bending moment diagram through this particular example. Now, here you see we have taken a beam, a simply supported beam, the end of this is hinged, let us call this as A, the other end is on roller which we call as B, and is subjected to a concentrated load P which is at a distance of A from the left support. So, and the length of the beam which we call as span is equals to L. Now, if we draw the free body diagram of the whole beam, now since this particular beam does not have any axial or the horizontal force. So, the horizontal reaction H A will be equals to 0 as we have seen earlier. So, we will have the vertical reactive force R A and the vertical reactive force at B which is R B. So, summation of horizontal forces equals to 0 gives us that H A is equals to 0. Summation of vertical forces equals to 0 gives us that R A plus R B is equals to the vertical load P which is acting. R A and R B is acting upward, P is acting downward. So, if we consider this as positive, so this is negative. So, R A plus R B minus P equals to 0 gives us R A plus R B equals to P. Now, if we take the moment of all the forces with respect to support A, then we have R B into L, this is in the anti-clockwise direction, and the load P causes bending moment in the clockwise direction. So, minus P into A, this is equals to 0. So, this gives us a value of R B as equals to P into A by L. Now, if R B is this, then the value of R A from this particular equation we can get that as R A is equals to P minus R B, and this is equals to P A into L minus P minus P A into L. So, this gives us that P, if we take it out, 1 minus A by L, and L minus A is nothing but B. So, this is equals to P B by L. So, the value of R B is P A by L and value of R A is P B by L. So, these are the two values of the reactive forces R A and R B. Now, what we are interested in is to plot the variation of the shear force and the bending moment along the length of the beam. So, we will have to look into different segments that what is the value of shear force and bending moment in those segments. And if we can place the ordinate the shear force values or the bending moment values in the ordinate along the length of the beam, the diagram thus we will get will give us the shear force or the bending moment diagram. Now, let us calculate the values of the shear force at different segments. Now, if we compute, let us say we take a section here, section 1 1, which is between A and let us call this point as C. Between A and C we cut the beam over here, and if we take the free body of this particular part, the left hand of this particular cut, then the free body will look like this. Here we have the reactive support R A. Now, on this part there is no load, external load, but on this section there will be stress resultant V and the moment M. Now, if we take the vertical equilibrium of the vertical forces, then V plus R A, this is equals to 0. So, this gives us the value of shear force is equals to minus R A, and R A is equals to, we have seen, is P B by L. So, this is equals to minus P B by L. So, this is the value of the shear force. Now, if you notice here that whether you take the section here or here or here or here or here up to the left edge of this particular load, everywhere we will get identical type of free body. So, this indicates that over the segment from A to C or just to the left of this particular load, everywhere the value of the shear will be equals to minus P B by L. So, it indicates that we have uniform shear force from A to the just left of this particular concentrated load. Now, if we like to find out the shear force just after this particular load, that means, if we take a section somewhere here and cut the beam and take the free body of the left part, then what do we get? Now, let us calculate that. Let us take the free body of this particular part. Now, here again we have the reactive force at the end A, which is R A, which we have seen as P B by L. Here we have the concentrated load, which is at a distance of A. Now, at this particular cut section, since this is the free body part, here again we have the stress resultants, they are V and the bending moment M. Now, if we take the vertical equilibrium of the forces, then V plus R A minus P, this is equals to 0, or the shear force V is equals to P minus R A, and R A, as we have seen, as equals to P B by L. So, this is equals to P minus P B by L. So, P if we take out, this is L minus B by A, that means, it is A by L. So, this is equals to P A by L. Now, please note here that on the left hand support left hand section of this concentrated load P, we had a value of shear force which is minus P B by L, and on the right of the load we have a value of the shear force which is equals to plus P A by L. So, that means, if we plot now the shear force, the ordinates. So, this is the length of the x. Now, at this point everywhere we have minus P B by L, minus we plot on the downward direction, on the negative of y direction. So, here everywhere we get the same value. So, it is a constant value over here. So, from here up to this left edge of the load is P B by L. Now, immediately after the concentrated load point, there is a change and we get a value of P A by L. So, from here to here there will be a change in the shear force value, and again wherever you take a section over here, you are going to get the value as P A by L. So, over this again it is constant up to this particular point, where R B again is given as P A by L. So, if you look into this variation of the shear force along the length of the beam, which looks like this. So, this is the diagram. So, this is the abscissa and these are the ordinate values, and this is the negative values and this is the positive value. So, this is nothing but the shear force variation, the variation of the shear force along the length of the beam because of the concentrated load which is acting at a distance of A. And from here immediately we can find out that what is the magnitude of the shear force acting at any section along the length of the beam. Consequently, what we can do is that we can compute the value of the bending moment, and if we calculate the value of the bending moment at this particular section, then the value of the bending moment comes as let us calculate the value of the bending moment. Now, if we take the moment of all these forces on this particular free body with respect to this particular section, then we have the bending moment m, which is in the anticlockwise direction. Then we have the clockwise moment because of R A. So, this is minus R A into x, and there are no other loads. So, this is equals to 0. So, this gives us a value of bending moment m as equals to R A into x, and R A we have obtained this as P B by L. So, this is equals to P B by L multiplied by x. Now, as you can see here that the moment is varying linearly with x. Now, when x is equals to 0, the bending moment is 0 at this particular point. Now, when x is equals to a, that means just at this load point or the left of the load point, x is equals to a. So, the magnitude of the bending moment becomes P B by L multiplied by a. So, that is the value of the bending moment at point C. So, m at C is equals to P A B by L. So, this is the value of the bending moment, and it is varying linearly as the value of x is increasing, the magnitude of the moment also is increasing from 0. X, when x is 0, bending moment is 0, and as the gradually the value of x is increasing, the value of the bending moment is linearly varying, and at a distance which is a from left end, the magnitude of the moment is equals to P A B by L. Now, what happens to the bending moment which is on the right hand side of this particular load? Now, let us calculate from the free body of the other part that what happens to the value of bending moment from this particular free body diagram. Now, if we take the moment of all the forces with respect to this particular point, let us call this as say D. Now, here the moment m, again the general moment m, which is at this section, which is in the anticlockwise direction. Now, the R A is causing a moment which is in the clockwise direction. So, minus R A into x. Now, load P, which is acting at a distance of a, also is causing a moment which is in the anticlockwise direction. So, this is plus P. Now, the load is at a distance of a, and we have taken the section from here which is at a distance of x. So, the distance of this load from this particular point where we are taking moment is x minus a. So, this is P into x minus a. So, this is equals to 0. So, the value of the bending moment m is equals to R A, which we have seen as P B by L times x plus P into x minus a. Now, here if we substitute the values, now this is valid, this particular expression is valid for x equals to a to L. Now, when x is equals to a, this part is equals to 0. So, and this becomes P B a by L or P A B by L, which matches with the value of the bending moment over here. So, that means, from this side we have computed the value of bending moment over here, which we have got as P A B by L. Now, the expression which we have obtained from this point to this point from this particular free body diagram, we find that the bending moment at this particular point C, substituting the value of x as equals to a, gives us the value of P A B by L. Now, what happens between these, since there are no loads? Now, if we substitute the x as equals to L, then what happens? Now, this is equals to, when x is equals to L, this is equals to P B plus P into x. Now, x here we have substituted as L, this is L minus a. So, the value of the bending moment which we are getting at this particular point is equals to we have computed the bending moment over here, which is m minus R A into x plus, this is in the again in the same direction, is equals to P into x minus a. So, this is going to be minus P b by L into x minus P into x minus a. So, this is minus, and L minus a is nothing but b. So, this is equals to 0. Now, L minus a is L is the whole length, a is this length. So, L minus a again is b. So, P b minus P b, this is equals to 0. So, the moment at this particular point again is going to be equals to 0. So, as you have seen that at this particular point the bending moment is 0, it is linearly varying going up to this particular point with the value of P a b by L. So, it is coming in this particular form, and again at from this particular general expression of this particular segment, we have here the value of the bending moment again as P a b by L when we substitute x equals to a, and when we substitute x equals to L, then we find the bending moment here as 0, and as it is expected that at the roller support and at the hinge support, the moment carrying capacity of this roller support and the beam supports, they are 0. So, the values of the bending moment at the hinge support and the roller support, they are expected to be 0. So, the variation of the bending moment along the length of the beam, as we can see, is in this triangular form, and this is what has been indicated over here. You see, this is the shear force and the bending moment diagram of this particular beam, which is loaded with the concentrated load P over the span L, over the length of the beam as L. If we have a concentrated load which is placed at a distance of a, we have the shear force variation. Now, as we have seen, the shear force here is I am sorry, this is negative. This is negative over here, this is negative and this is positive. Now, for the bending moment, as we have seen, is the positive for the whole region. So, this we have taken as our the abscissa, the direction of the beam, and these are the ordinate. This is the positive direction and this is the negative direction, and here again this is the length of the beam and this is the ordinate of the bending moment. So, the diagram over the length of the beam which we get, this we call as the bending moment BM diagram, and this we call as the shear force diagram SFD. And as we have seen that the value of this is equals to the reactive force, which is equals to P b by L, and the value of this here is P a by L. So, this is the diagram with the ordinate value given gives us the shear force diagram, and the bending moment, as we have seen over here, the value of this is equals to P a b by L, and that is the largest magnitude of the bending moment over here, and in all other places the values of the bending moment is less than this value of P a b by L. Also, if we look into that along this this particular segment between 0 to a, the slope of the beam is a positive slope, because the larger value minus the lower value will give a positive value over this length, the dm dx, and as it is expected that dm dx is equals to minus v, dm dx is equals to minus v. So, now here the moment is P a b by L, here it is 0. So, and over the length L. So, the value of dm dx is P a b by L divided by a is equals to P b by L. So, here it is expected that it will be minus P b by L is the as minus v. So, this is nothing but v here is shear force P b by L, which is minus of v over here. So, over this particular segment it indicates that the slope of the bending moment is equals to the negative of the shear force, and on this side again the slope will be negative, since we have lower value on the right hand side with respect to the left hand side. So, the slope is negative, and so minus dm dx we will get, which is equals to minus v, eventually it will become plus v, and so the value over here is equals to P a by L. So, in fact, from this particular diagram you can observe that when a simply supported beam is subjected to a concentrated load which is at a distance of a from the left support, how the shear force and the bending moment varies, and the relationship between the shear force and bending moment as we have obtained through those differential form, they also can be visualized to be satisfied in this particular through this particular example. Now, we have looked into that where there are no loads on the beam, there the shear force is constant and the bending moment is varying linearly, and from the concentrated load point there is a jump in the shear force from the left hand to the right hand support, and from the bending moment diagram you can look into that at the concentrated load point virtually there is no change in the bending moment is the same, but there is a change in the slope. On the left hand side you have the slope which we call as a positive slope, whereas on the right hand side we have a negative slope, and there is a jump in the rate of change of the bending moment value. Now, let us look into that if a simply supported beam instead of a concentrated load is subjected to a uniformly distributed load of intensity q over the length L, then what happens to the shear force and the bending moment diagram. Now, here as usual again we have the reactive forces acting, let us call this end as A, this end as B, and here the reactive force which is acting is R B, this as R A, and we have the horizontal force H A. Now, again from summation of horizontal force is equals to 0 gives us that H A is equals to 0. Now, summation of vertical forces equals to 0 will give us that R A plus R B is equals to Q times L, which is the vertical load acting in the opposite direction of R A and R B. So, now if we take the moment, let us call this equation as 1. Now, if we take the moment of all the forces with respect to A, if we say moment about A is equals to 0, we have R B into L, which is in the anti-clockwise direction, is equals to Q times L, which is in the clockwise direction, times L by 2. So, this gives us a value of R B as equals to Q L by 2, and from equation 1 we can write that R A is equals to Q L minus Q L by 2, which is equals to Q L by 2, and from this particular diagram also we can visualize this being a symmetrical one, that R A is equals to R B is equals to Q L by 2. Now, the total load is Q times L, and half of the load is getting distributed or shared by R A and R B. Now, supposing if we take a section here which is at a distance of x and draw the free body diagram of the left part of this particular beam, then we have this particular beam with the reactive force which is Q L by 2. We have the distributed load over this particular segment, and let us call this distance as x, and on this particular side we have the stress resultant shear as V and the bending moment as M. Now, if we take the vertical equilibrium of all the vertical forces, then we have V plus Q L by 2 minus Q times x, this is equals to 0. So, this gives us that V is equals to Q x minus Q L by 2. Now, here you please note that if x is equals to 0, which is the left support, then V is equals to a value of minus Q L by 2. Now, as x goes along the length of the beam, when x becomes L by 2, then the value of V becomes 0. Now, as x increases, naturally this particular quantity keeps on increasing from minus Q L by 2, and then at the x equal to L by 2 it becomes 0, and at x equals to L this becomes V as equals to plus Q L by 2. So, you see the variation is like this. If we take the center over here as this particular point, then over the point x equal to 0 we have a value of ordinate as minus Q L by 2, at L by 2 we have value of ordinate as 0, at L we have value of ordinate as Q L by 2. So, if we join these three linearly, since it is varying linearly with x, we get the shear force diagram. So, this is the shear force diagram for this kind of loading, and here we do not have as such any change in the loading. So, this will give us the value of the shear force. Now, if you compute the value of the bending moment, then the bending moment at this particular section is M. If we take the moment of all the forces with respect to this particular section. So, M which is anti-clockwise, Q L by 2 is clockwise. So, minus Q L by 2 into x, and this is also anti-clockwise. So, minus Q x square by 2, this is equals to 0. So, this is plus. So, m is equals to q L by 2 x minus q x square by 2. Now, here if we substitute the value of x, now at x equal to 0, moment is 0, which is expected at the hinge support. At x equals to L, again the moment is 0, and at x equals to L by 2, you get a value of q L square by 4 minus q L square by 8. So, this is equals to q L square by 8 at the mid span. So, if we plot the variation of the bending moment, we get a parabolic distribution. So, q L square by 8 here, 0 here and 0 here. This is of course, it will be in the opposite direction, because this is positive everywhere. Now, this is the diagram of the shear force and the bending moment as we have evaluated right now. This is the shear force diagram, which is negative here and positive here, and this whole thing is positive. Now, please note over here that the slope of this bending moment diagram at L by 2, here the tangent to the diagram is horizontal, and correspondingly the shear force value here is 0, and that is what we get, that if you have dm dx, if this v is equals to 0, then dm dx is going to be constant, the moment is constant, and the slope over here is the horizontal one. So, this diagram we call as the shear force diagram, and this diagram we call as the bending moment diagram. Well, we have some example problem set for you. Please look into this. We will be discussing in the next class to draw the shear force and bending moment diagram for this kind of a loading, to draw the shear force and bending moment diagram for this kind of a loading, that if we have beam, simply supported beam subjected to a concentrated moment, then what will be the values of the shear force and bending moment over the length of the beam. And then if we have a cantilever beam subjected to uniformly distributed load, then what will be the shear force and the bending moment diagram for this particular beam. Well, now to summarize, then in this particular lesson, what we have done is that we have recapitulated the previous lessons aspects. So, whatever we have looked into in the previous lesson, here we have discussed those aspects again, and we have looked into the concept of drawing shear force and the bending moment diagrams. Also, we have looked into some examples on how to plot the shear force and bending moment diagram if you have a concentrated load or uniformly distributed load over the length of the beam. Now, these are the questions given for you. What is the value of shear force where tangent to the bending moment diagram is horizontal? What is the value of bending moment in a hinge and a roller support? And what is the effect of concentrated moment at a point in a beam on shear force at that particular point? The answers will be given in the next lesson. Thank you.